All right, guys. Well, this is your second video lesson, but this is the one that we're going to start doing here while we're in hybrid, so that you guys at home can get the same lesson as you guys at school, and Mr. Lampkin doesn't have to teach it 4 times. So that's the bonus. But remember, we will always take questions when you're live before you take your quizzes and all that good stuff. So chapter 3 is all about exponential functions and logs. So it starts out, 3.1 starts out with exponential functions and their graphs. So I want to take a look at, this is the sort of the parent function, the standard form. A is the base of the exponent. We know this is an exponential function because x is in the exponent. So a is a number, and it has to be positive. That's the first thing. You cannot have a negative base. That's important to remember, especially when we start talking about logs, because it will affect the logarithms domain. But not only has to be positive, it cannot equal 1. Because if it's 1, then you're just flatlined. You got a constant function. So the base has to be something that can either grow or decay, depending, right? If a is between, so if it's greater than 0 but less than 1, we're talking decay. And if it's greater than 1, we're talking growth. Also important, right? And it affects the graph as well. X can be any real number. X is any real number you want it to be. So it can be a decimal. We have rational exponents. We have all sorts of things. So let's just take a look at a graph of an exponential function. We'll just do 2 to the x here, something simple to get started. And when we talk about domain, we know it's all reals. And the range now, because when x is negative, what happens to the base is that it flips. So it becomes 1/2. And so then when 1/2 times a half times a half, as you're doing the exponent function, it's just going to keep getting smaller and smaller and smaller and keep continually approaching 0. So we have this horizontal asymptote right here at 0. And because that's always positive, this is always going to be above the y-axis. So now we have this horizontal asymptote. The other thing that we know is that when x is 0, we're going to be 2 to the 0 or 1. So we have a y-intercept at 0, 1. No x-intercepts. And this function, because this base is greater than 1, we have growth, which means this function is increasing everywhere. And the nature of exponential functions is that when x is small, it's not going to grow as fast. Take, for example, a penny. If I let you double a penny, well, the second day, right, every day you're going to double the penny. I give you 1 cent, you double it. I give you 2 the second day, and then it becomes 8, and then it becomes 16 cents, and then it becomes 32. So I mean, you're doubling. You get 32 cents, on the 5th day. Still not a lot of money, right? On the 7th day, you're like 128 pennies. So you got $1.28. Woohoo, right? But when you get to the 30th day, so you think, okay, I've gone a week, and I only have $1.28. But on the 30th day, you have 2 to the 30th power. And 2 to the 30th power is like in the millions of cents. So it does start out slow. We already know what happens when x gets negative. This thing starts to approach y equals 0. And then here it's going to go and then really start to take off. So that's what the graph of an exponential looks like. So what we do with that, obviously, is that we can start transforming it. For example, we can flip this thing. Like, what if I replace x with negative x? Now what we know is that because of the negative exponent, when x is negative, this will be positive, so it's growing this way. And it's coming down, and we're still going through 0, 1, but when x is positive, this thing's going to start to go to 0. So by flipping the base with the negative exponent, we actually, again, replacing x with negative x makes you reflect over y, right? So this is exponential decay. Another way to write that. This would be the same graph if we did 1/2 to the x power. So keep that in mind. There's two ways to write that particular graph. Again, the transformations that we always study never change. If we put a number out front of my 2 to the x, we're going to get a vertical stretch. So it's going to just make it go, because we're tripling everything after we do our 2 to the x, this thing's going to hit 3 and go up a little faster. Because normally it'd be 1, but now because of this, it's going to go through 0, 3. So the vertical stretch, we can also shift the asymptote up and down by just shifting the graph up and down. If I take 2 to the x plus 4, then that's going to take my vertical asymptote up 4 units. And then we're going to go through 0, 5 and up. And likewise, if you put a negative out front, like negative 2 to the x, not negative 2, but 2 to the x, and then the opposite of that. So really, we're making y negative, which is going to do what? It's going to flip this thing over. Instead of going this way, it's going to come this way. So that's the reflection over the x-axis. So again, the transformations all stay the same. If we take my function and I do an x plus 2 in the exponent, you guessed it, it's going to shift it 2 units to the left. So where this point was at 0, 1, now it's going to be at negative 2, 1. And so it's just going to take that whole graph and just shift it left. So again, all the transformations with these functions all work the same. The reflections, the translations, we can stretch and shrink and all that good stuff. Okay, so I want to shift gears real quick and talk about an application of an exponential function, because with banks, sometimes you get, obviously you put your money in a bank, you get interest. And with the stock market and everything else, money can start to compound. And what that means is your money is growing, and so you're reinvesting that growth, and then that's going to grow even greater, right? So you can get this sort of exponential growth happening with compounded interest. So there's a formula, a general compound interest formula, which looks like this. So that's the amount is equal to the principal, which is the amount of money invested. 1, because you're getting 100% of your money. Your interest rate that they give you over the number of times that you're compounding, and I'll explain that in a minute. And then to the NT power. So I'm hoping that you've seen this before. But what we got going on, again, this is my investment. That's because I get 100% of my investment plus whatever my interest rate is, and that's got to be a decimal. So that's my rate as a decimal. And then this represents the number of times we compound per year. So number of compoundings. And then T is my time in years. So let's say I go to the bank and I put in $500 and I get a 2% interest rate, which is way better than what they're giving. But this bank is only going to do it annually. So then my compounding would only be 1 because I'm only going to calculate my interest one time. And let's say I want to check it in 5 years to see how much money I've made. So when looking at this, get my calculator out here. So I got 500 times 1 plus 0.02 to the fifth power. Whoops. I got a natural log in there somehow. Hang on. All right. There we go. So at the end of 5 years, I'm going to have $552.04. Okay, not bad, right? Not bad. However, let's say the bank down the road wants your money, and so they're saying, you know what, we're going to compound quarterly. So by compounding quarterly, they're going to take your interest rate, 0.02, and they're going to divide it by 4, because quarterly means once every 3 months or 4 times a year. And then now, instead of in 5 years, instead of just doing it 5 times, you're going to do it 4 times each year for the 5 years. So now you're at 4 times 5, or 20 times they're going to calculate your interest. So let's try to understand what's happening here. So at the end of 3 months, the first 3-month period, they're going to give you 1/4 of your 2%. You say whoop-de-doo, but that's a little bit of money, and it's going to get added to your principal the next time they go to calculate. You're not going to be based it on 500, it's going to be based on 500 plus a little bit more. So when we do this calculation, and you got to be careful how you enter this stuff into your calculator. So we have 500, and it's 1 plus 0.02 divided by 4, close parenthesis, to the 20th power. And now we're at 552.44. So we made a whole 40 cents more. That's fantastic, right? The bank on the other side of town says, you know what? We're going to compound your interest daily. So that's 365 times they're going to do this. So you would think this would jump up. And now it's 365 times 5 in the exponent. And that's a big exponent, but that number is getting smaller and smaller and smaller, isn't it? So let's take a look. Okay, so we got 500 times 1 plus 0.02 divided by 365 to the 365 times 5 power. And we get a whopping $552.58. So even though we jumped from quarterly to daily, we only went up about 14 cents. So mathematically speaking, I would ask you all the question right now, is that something's going on here. Even though this exponent's getting really large, 1 plus very small, this number is getting closer and closer to 1. So it's not having as big of an effect. So it's slowing its rate of growth. It's slowing its rate of growth, which means we're probably approaching some sort of asymptote. So interested minds want to know, what would that asymptote be? Well, we have to take out, if we're going to try to figure out if there's a specific value that we're approaching, we got to remove all these things that we've thrown in, like the 500. So I'm going to invest $1. I don't want to affect it in any way. And I'm going to get the highest interest rate I possibly can, which would be 100, right? And then I'm going to just look at this over 1 year. So I want to see what's going on here. So I'm going to put in specific values of n. So when n is 10, and then I'm going to jump to like 1,000, and then I'm going to jump to 1,000,000. And just kind of see what that number starts looking like. So I'm going to type this in. Bear with me. So we got 1 plus 1 over 10 to the 10th power. And we get about 2.59374. Interesting. Okay, now I'm going to let n be 1,000. So I've got 1 plus 1 over 1,000 to the 1,000 power. 2.716923. So yes, it's getting bigger. Now let's put in 1,000,000. So we have 1 plus 1 divided by 1,000,000. 1,000,000. And we get 2.71828. Interesting. Now at this point, I would ask you, anybody recognize that number or seen that number before? Well, that is Euler's number. That is E. E is about 2.71828, like we got. Then it goes 182, blah, blah, blah. So E is a number like pi. It's irrational. So that decimal goes on forever and ever and ever, never repeats, never ends. But the significance of this process, like what are we doing? We're letting n get bigger and bigger and bigger, and we keep approaching this number. This is our limiting value. So if we look at the limit as n goes to infinity of this 1 plus 1 over n to the n power, we get E. And because we're using a compound interest formula, right? That's what this is. And we're letting the number of times that we compound. So we're going by the day, by the hour, by the minute, by the second, or if we reach this limit, we are continuously non-stop compounding. Non-stop. Continuous. Sounds like instantaneous rates of growth, which is exactly what this is. So, gang, what this means is that e to the x is a function, right? Its graph looks, similar to 2 to the x because that's very close to 2. But if I wanted to find the derivative of e to the x, guess what? Because e is already a continuous growth, like instantaneous growth on this exponential curve, it is its own derivative. Pretty freaky. But exactly what's going on here, right? So, we start looking at E because in our growth models or our decay models in the real world, things don't just like grow, stop. They continuously grow or they continuously decay. You've heard of half-lives, right? So what is a half-life? A half-life is how many years it takes for something to decay to half of what its original amount was. Well, take like a Twinkie, for example, sitting on a shelf. Let's say it's got a half-life of 10,000 years. So what does that mean? That Twinkie is sitting there, it's all good, and then in 10,000 years, all of a sudden, half of it disappears? No, it's decaying continuously over that, right? That's just how long it takes before half of it's been gone. So, so whenever we start talking about continuous growth or this equation, because if we bring back in our investment, and then E becomes the base, and remember what we're talking about here, right? E becomes this whole thing minus the interest rate. So we just raise that to the r times t power, and we get PERT, which is our continuous interest formula. All right, so let's go back to our example. Let's say somebody down the street said, you know what, I'm going to compound it continuously. It's never going to stop. You would take your $500 and you would go 0.02 times 5, and we would get $500 e to the 5 times 0.02 power, $552.58, which, remember when we compounded it daily? Now, I didn't give you these other decimals here, but this one's going to be just a touch less than this if we were to continue the decimals. But if we're talking money, we're just cutting it off right there. So yes, that's a bigger number, but again, it's slowed way down. And this is the maximum value you're going to be able to get in that situation. So, moral of the story, if it's continuous growth, continuous interest, we use that. If it's compounded, we use this. Okay, so finally, got a couple things left to talk about. And again, we've talked about this before, but exponential functions are one-to-one because their inverse functions are logarithms, and because the base of the exponent has to be positive, then we don't have any domain issues with our logs. So, and we know what one-to-one means. So that if I have a situation where I have an equation I'm trying to solve that looks like that, if I can rewrite this number in terms of something that has a base of 5, then I can utilize my one-to-one property. And since 125 is 5 cubed, but it's flipped, so that's 5 to the negative 3 power. And now I can use my one-to-one property and set x minus 2 equal to negative 3 and just solve for x without any concerns. Sometimes you'll see equations like this. We have, and again, it doesn't matter what the base is as long as you can, like both these bases are the same. So for me to solve this, or for this to be equal, I know that these exponents have to be equal. So now I got a quadratic, so I got to set it equal to 0, factor, and I get 3 or negative 1, and both answers work without issue. So those are the main ideas in section 3.1 that you guys have to be able to do. You have to be able to graph it. You have to be able to transform the graph based on the equation. You have to understand when you have growth, when you have decay, and then you also have to be able to utilize the application of the compound interest formula and the continuous interest formula. All right, that's 3.1.